Welcome everyone. Today we're going to discuss multi-directional structures. First we're going to do a little bit of review on some of the topics that we've covered so far. So in this course so far we have talked about ways to describe fluid flow and also ways to describe bed forms. So when we're thinking about fluid flow, we've talked about the Reynolds number, the Froude number, and Stokes' law of settling. And you've used some of those numbers to describe different parts of bed form diagrams. We've also talked about sediment transport, Bernoulli's principle and Newton's laws, and how they describe lift and drag on particles, and the Holstrom diagram and how we can use that to interpret when sediments are eroded, transported, and deposited. We've also talked about bed forms. So again, bed forms are the surface that we see. So I've illustrated that here, a bed form, versus stratification are the structures we see in cross-section. That's the side view of our sediment or rock layers. The bed form is the 3D structure on the surface of the sediment. So you can imagine snorkeling in the water or flying overhead and looking down, and what you see is the bed forms. And if you were to dig a trench or see an outcrop, what you often see is the stratification. So here we have tabular crossbeds, here we have trough crossbeds. So the bed form are these sinuous crested ripples, and the crossbeds you see in stratification. We've also talked about a variety of different sedimentary structures. One thing I really want to remind you of is the difference between ripples and dunes. So you can refer back to this slide. These are all things we've talked about before. Okay, so for today, we want to think about how waves interact with the seafloor. And waves are of interest to us because they're going to be forming these oscillatory ripples. Waves are moving in and out in two directions, so they're going to produce some unique sedimentary structures. So the first thing you have to understand is how waves interact with the seafloor. So the figure on the left here is showing the circular motion of a wave in the open ocean. In the open ocean, waves are moving in an oscillatory manner. It is circular. Where the water depth is less than half of the wavelength, that's when the water starts to interact with the sediments on the bed. And that's what we call wave base. When the water starts to interact with the bed, that's what we're calling wave base. So here you can see the water surface, and you can see a trough, a crest, and a trough. So that distance from trough to crest to trough, that's the wavelength. And when the distance, the depth of the water is less than half of that wavelength from trough to crest to trough, that's when the wave is going to start interacting with the sediment. And when waves interact with the seafloor, we talk about wave base. Again, that wave base is where the waves are interfering with the sediment. And we have two wave bases. Fair weather wave base, so that is anything from this point and higher. That's where regular waves interact with the sediment. And then we have storm wave base. Any place from this point to the fair weather wave base bottom. So in between these 2 points, that's our storm wave base. So typical ocean waves have a wavelength between 10 and 30 meters. And so if you divide that by 2, right, because the wave base is half of that wave length of the wave base is going to be between 5 to 15 meters depth. So if you're out swimming between 5 and 15 meters depth, you're within that region of fair weather wave base, normal ocean waves. Large storm waves can have much greater wavelengths, up to 400 meters. And so the storm wave base can go down 30 to 125 or greater meters in depth. And that is this region here. The difference between fair weather wave base and all the way down to the deepest point where storm waves may be able to interact with these sediments on the bottom of the ocean. And these different types of waves, typical ocean waves and large storm waves, leave behind different sedimentary structures. So we're going to explore some of those now. So wave ripples form in oscillatory water, and that's created by these fair weather waves that we've been speaking about. Wave ripples have a symmetrical profile, and you're already familiar with that idea from the lab. They often have a sharp crest, so that it's really quite pointy, where the two sides of the ripple come together at that point. It's often very sharp. And in wave ripples, you'll often see this tuning fork bifurcation. So you'll see the crest of the ripple suddenly split into two separate crests. So you can see that here. Here's a single crest, and then at this point it splits into two crests. So it's similar to the shape of a tuning fork, which is used to tune instruments. Here's another set of examples of some of those wave ripples. Again, these are forming an oscillatory water created by fair weather waves. You can see here some of these sharp crests of these oscillatory ripples. And again, on the bed form, you'll see these sharp crests and this tuning fork bifurcation. So here's our cross stratification, and here's our bed form on the right-hand side. We can also watch a quick video about how these ripples form. Great, so we were just able to watch how the sediments are moving in the water column and how a slight disturbance to the surface can form these wave ripples, and you can watch them propagate. So here we have a cross-section showing wave ripples. So I want you to look at the diagram on the right-hand side and then compare that to what you're seeing on the left-hand side. In the right-hand side, you're seeing these wave-formed current ripples, and the laminae can sometimes be opposed. We have laminae moving in one direction and the other direction. It kind of depends on the ripple that you're looking at. So laminae here moving toward the right, laminae here moving toward the left. You can also have these chevron interlaminae, where you can see laminae have been cut off and then replaced, leaving these little triangles behind within the crest of the ripple. We also have sediment draping over on top of the ripple. So can you see any of those features in the photo on the left-hand side? I'll highlight some of them for you since it's the first time looking at these. Here is some draping sediment. Let's look at that again without the highlight. Do you see that sediment drape? Do you notice the cross stratification is never cut off? We have laminae, but they have this undulatory shape. That's the draping. Do you also see some unidirectional laminae? I see some right here. We know that the water was moving toward the right based on the direction of the slope of the forceps. But in the next ripple, the water is moving toward the left based on the direction of the forceps. So we have these symmetrically shaped ripples, but the cross stratification within them is moving in different directions, and they are often draped by these undulatory laminae. So those are simple symmetrical oscillation ripples, but there are lots of times where water, especially along the beach, is moving in multiple directions. The waves are moving in and out, but we also have a longshore current. So that longshore current is caused by waves moving in and out at an oblique angle. They're not perfectly perpendicular to the shoreline, they're coming in at an angle to the shoreline. And so on average, there's a general direction of wave propagation, and that forms this longshore current. And you've probably experienced this if you've spent some time swimming in the ocean. You'll find yourself slowly drifting down along the beach. So if the longshore current is strong and storms are weak, shore-face deposits can include these migrating dunes that are perpendicular to the shoreline. And we'll talk more about this as we talk about beach facies in the future. But we have this idea here that there is wave action moving in and out, but there's also some direction of motion, the longshore current. So we're going to get a combination of these symmetrical oscillatory waves with a preferential single direction along that longshore current. So here's another example of a multidirectional bed form. This is called herringbone cross stratification because it sort of looks like the bones of a fish, the ribs of a fish coming together to meet the backbone. So they are this chevron pattern of parallel lines, these parallel forceps that are perpendicular to the parallel forceps below them. So you have evidence that water was moving to the left, then to the right, and then to the left in this illustration. So then compare that to the photo on the left-hand side. Which direction was the water moving? In the bottommost bed, you can see, based on the direction of the forceps, that the water was moving to the left. In the nextmost bed, based on the direction of the forceps, you can see the water was moving to the right, then again to the left, and then again to the right. And the way that these cross strata truncate one another and are similar in size and in angle, but in opposing directions, gives us this herringbone shape. So we know that the water was moving in two directions and at 180 degrees, so equally moving both in and out. This could be the result of a surge inland where water is moving in, then a delay, and then return of the tide back to sea. That's causing one direction and then an equal amount of motion in the opposite direction. What you don't want to confuse these structures with are troughs. You really want to look for the planar structure, right? The bed forms here, the bedding surfaces are planar, a planar line in between these opposing cross strata or forceps, versus trough cross stratification, which would have these troughs or circular structures. We're not seeing that here. We're seeing planar lines for each bedding surface. Another multi-directional bed form are interference ripples. So interference ripples form when we have flow in two directions, but at an angle to one another. So you can see this very interesting pattern here is representative of flow moving in two directions at an angle, often at a 90-degree angle. So you have a surge moving in and then water flowing back out to sea at a different angle, and it will form this bed form on the surface. When we have water moving in and out, we can have both construction and erosion of our ripples. So as the tide moves in and out, we can have construction in one direction and then destruction or erosion as the tide recedes. So I'll show you this step by step. here's a constructional event. So here's our normal ripples, the forceps here indicating that flow is moving from left to right. And so all of these ripples are propagating from left to right as the tide comes in. But as the tide goes out, we can have destruction of these ripples. The sediment is being eroded, so we're smoothing out these ripples. As the tide comes back in again, the ripples start to reform, but see how they're slightly to the right-hand side of where they used to be, and the forceps don't quite line up between the first set of ripple laminae and the second set of ripple laminae. So here's our dominant tidal phase constructing ripples, and then our tide is moving out. It has less energy when it's moving out, and so it's mostly just removing sediment, not necessarily carrying new sediment to deposit it. And so it is weathering away some of these ripples. So these are reactivation surfaces. This line here, where we can see these ripples are moving the same direction, but the forceps aren't quite aligned with one another. So they represent two different surges, two different periods of ripple construction. So in real life, it can look something like this. Here's another diagram of what a reactivation surface might look like. Here are our forceps, and you can see this reactivation surface because the second set of forceps aren't necessarily the same thickness, and they don't quite line up with the forceps below this surface. So an example of one of those in the picture on the left is here. We have a heavy mineral lag that is forming on this reactivation surface. So we had one ripple propagating here, and then a new set of beds forming in more this orange color on top. And here's a mineral lag that is formed at that reactivation surface. So a mineral lag might be something you look for because this less dominant subordinate tidal phase on the way out is not as strong, and so won't be able to carry those heavy minerals. It'll leave them behind and maybe carry the lighter minerals out to sea as it's eroding. So leaving behind this heavy mineral lag. So that could be one way to identify a reactivation surface. The other is to look for a surface that is separating two sets of laminae and causing them to not quite line up with one another. Okay, so all of these structures that we've just spoken about are interference ripples, our herringbone cross-stratification, our symmetrical oscillation ripples. They all form in the fair weather wave base region. So wave ripples, herringbone, interference ripples, reactivation surfaces, these are all occurring here above fair weather wave base. So now we want to talk about structures that form below fair weather wave base in that storm wave base region. And the major structure we see here is called hummocky cross stratification, and it's indicative of deposition by storm waves. So you're seeing an example, an illustration here of what hummocky cross stratification looks like. It's characterized by wavelengths of 1 to 5 meters. So you can see from this photo, here's a person for scale. This structure is quite large, many meters in distance. It's characterized by these hummocks and swales. So the hummock has a three-dimensional concave down structure. Here, the swale, a concave up structure. So you're looking for this lens shape, a lens-shaped structure, which you can see here. The beds have a lens-shaped structure to them, all of these laminations. What is different in hummocky cross-stratification is that it's not planed off. It's not eroded at the top. We have these concave structures in two directions. And the cross laminae will be in multiple directions, moving to the left and the right, the back and the front, because storm waves can be very turbulent, moving in multiple directions. So that's another way to characterize hummocky cross stratification. And these hummocky cross strata are not found in normal fair weather wave base areas because normal waves after a storm will erode away any of these storm-like structures that form and replace them with regular wave ripples or interference ripples, etc. The other thing to know about hummocky cross stratification is the type of sand. it tends to only form in medium or fine sand. And again, very important, when you see hummocky cross stratification, it indicates we're below fair weather wave base. Here are some additional pictures of hummocky cross stratification. Again, it's due to the influence of storm waves, and you'll often see it as these sandstone units in between mudstone units. You can think of the deeper part of the shore face being quieter in energy, so more mud dominated, and these storms bringing in sandy units because they are more high energy and can carry the coarser grained sand compared to the mud. So often these sand units, these hummocky cross-stratified beds, will erode into the sediment, and they'll leave behind these sole marks, these gutter casts, from the scouring by the storm waves. And we'll talk more about gutter casts next week. So these are all ways to identify some hummocky cross-stratification. I want you to also compare this to trough crossbeds, which we've spoken about before. Here again is our diagram on the left of hummocky cross-stratification, where you can see this lens-shaped structure. We have concave up and concave down laminae. This is in contrast to trough crossbeds in stratification, where all of the structures are concave up. They're all facing toward the surface. All the laminae are in this similar scoop shape. You're never seeing any of these concave down structures like we see in hummocky cross-stratification. That's not present here because each of these scoops is eroding away the layer below it, but this is not doing that. Here we have both the concave up and the concave down structures. Okay, so again, just to remind you, in the fair weather wave base region, we're depositing things like wave ripples, herringbone, and interference ripples, and deeper on the shore face, we have the storm wave base region, where we see hummocky cross stratification and gutter casts from the erosion due to storm waves. Heterolithic stratification is this idea that we can have different types of sediments interbedded with one another. So hetero is for different, lithic, of course, for sediment, and stratification is the layering. So there are three types of heterolithic stratification. One of those is flazer bedding, where we have sand with ripples, which you can see the four sets here, with a little bit of mud, these darker areas, draped in between those rippled sands. Wavy bedding, where again you can see some ripples, but we have an even amount of mud in between those ripples, so 50-50 mud and sand. And then lenticular bedding, where we have some isolated sand ripples, these lenses or lenticles, and a lot of mud. So the thing you want to think about with heterolithic stratification is how are you going to mix sand and mud? What conditions are we going to have where sand ripples and also mud might intermix with one another? Let's look at some real-life pictures of heterolithic stratification. On the left-hand side, you're seeing flazer bedding. Remember, flazer bedding is where we have rippled sand with a little bit of mud. So you can see this is primarily sand with some thin mud horizons. Then we move into wavy bedding. So you can see the increased proportion of mud in this wavy bedding. So we have these sand ripples with thicker mud drapes. Sand ripples with thicker mud drapes. Ooh. Here again is our wavy bedding, our sand ripples with thicker mud drapes. Sand ripples, thicker mud drapes, moving into lenticular. And in lenticular bedding, it's primarily this dark mud, and then we have little lenses of sand. So what environment might we be mixing sand and mud together? What conditions, what flow velocities, what type of real-world environments might we have interbeds of sand and mud, sand and mud? I'll let you think about that one. We'll discuss in class. The final thing to know is a way to document flow directions. When we see these oscillatory structures, ripples, crossbeds of different kinds, we can communicate the general flow direction through what are called rose diagrams. So these rose diagrams are a way to show flow direction on a compass. So out in the field, you have your compass, and you are able to map the direction of the forceps or the direction of the bed forms, and then plot them on a Rose diagram. You'll see that each of these diagrams have an N number. That's the number of samples or the number of distinct observations that were made. And then for each of those, it's plotted what direction was the current moving. So for example, in this figure, figure D, we can see that the water was moving toward the north and east and toward the south and west. So this is an oscillatory structure. We have an even amount of motion toward the northeast and toward the southwest. And so each of the thicknesses and durations of the line represent what proportion of the observations were moving in that direction. You could contrast this with something like figure E, which still shows the most of the motion toward the northeast and toward the southwest, but also has a component of motion toward the southeast and the northwest. So we have oscillatory motion in multiple directions. Here in figure F, this is really showing motion mostly in one direction, toward the southwest. So you can see how these Rose diagrams allow us to plot and represent the primary flow direction based on observations from the field. So looking at over here, these flow directions, what is the primary type of flow? Is it unimodal, mostly in one direction? Or is it bimodal, in two directions? Or is it polymodal, like figure E, in many directions? So take a look at these figures here and have an idea of what kind of direction the paleocurrent was flowing in. All right, you should be all ready now to identify multiple types of bed forms and sedimentary structures. Good luck!